So today we're going to talk about power supply theory, and we're going to break this up into multiple sections. We're first going to talk about all the components on the primary. We're then going to talk about the three different power supplies that are shown here that are on the secondary. So we're going to talk about the half wave power supply, the full wave power supply, which can also be called full wave center tap, and the full wave bridge rectifier. We're going to get into filtration, rectification, and in the next rotation, we're going to get into another term called regulation. But essentially, why do we need power supplies? Can anybody tell us what a power supply is for? Who wants to take a guess at why we have a power supply in just about every electronic device that we have? Okay, so Jeremy says taking AC and putting DC in the circuit. Well, that's a correct answer. Let's do a pretty broad definition of a power supply. It's a device that supplies the required voltages for our electronic device. Now let's use some examples. You guys are all doing computer class, and we know that the power supply in a computer puts out 5 volts and 12 volts for the drives, the motherboard, and all the internal components in a desktop computer. It takes 120 volts from the wall, which is alternating current, and it steps those voltages down, turns them into DC to power the circuits that we need. But then there's other devices that require higher voltages. Let's take an appliance that we all have at home. We all have a microwave oven. That plugs into the wall and takes 120 volts, and that has to step it up to about 2000 volts because there's something in there called a magnetron tube that requires high voltage. And it's 2000 volts DC, so it steps the voltage up, turns it into DC, as well as low voltages for like the little digital display and the control panel that's on your microwave. So essentially, a power supply is a device that interfaces with our AC power and turns it into the voltages and currents that we need to run our device. Now, don't forget, not every device plugs into the wall because we do have plenty of things that work on batteries, like our cell phones and our laptops and other portable devices, but they still need AC power supplies that convert it into DC to do the charging. Still at the end of the day, we're plugging our phone into the wall or our laptop into the wall and converting it to DC and the required voltage to charge that device. So the power supply takes our AC voltage from the wall socket and turns it into the voltages and currents that are required to power our device. So what we're going to do is we're going to go through the primary of our power supply here. So we're basically going to look at this transformer core and everything to the left today. So we're going to talk about everything in this little area. We're going to call that the primary side. So let's start at the very beginning. We have an AC plug. We have 120 volts alternating current, RMS, at 60 hertz coming out of the wall. And the first component that we're going to encounter is a protection fuse. What is the job of our protection fuse? Moses? Very good. So essentially, if for some reason too much current flows through a fuse, he says it blows. Well, if you look inside a fuse, what does it look like? A very thin piece of wire, a very thin piece of metal. It's basically a small conductor that can carry just enough flow through it, just enough current. And if it exceeds that value, it overheats and melts. Now, sometimes you'll see a fuse that just has a little break in the wire. And other times you'll see the whole fuse turn black and silver and has all this melted metal in it. It all depends on how much current flowed through it. Maybe there was a short circuit or a big power surge, and that fuse blew violently. On the other hand, sometimes fuses just fatigue over time, and they get a little break in them, and you can just pop that fuse in, and the thing works again. Nonetheless, the fuse is there to protect us. If something shorts out in the device and draws heavy current, we don't want those components to overheat, potentially catch on fire, and cause catastrophic damage. That can happen if there's a short circuit. So we have a protection fuse. This next component, does anybody remember what this guy is? Andrew. It's a varistor. Metal oxide varistor, or MOV. Does anybody know what a metal oxide varistor does? So this component, as it sits in this circuit, is pretty much not doing anything. Day in and day out, it just sits there and does nothing. You can see I put right above it, I'll highlight it here with my little round red highlighter, 150 volts RMS. So this is a 150 volt varistor. Essentially, it exhibits a really high resistance across our power line. It's actually like a couple of Zener diodes back to back. And we know that Zener diodes, when you put enough voltage in the back bias mode, they have an avalanche effect and allow some current to flow backwards through that Zener diode. Well, that's what these guys do. A metal oxide varistor exhibits a lot of resistance when voltage across it is below its rating. Now, we have 120 volts coming out of the wall and 150 volt varistor, so it's just sitting there pretty much doing nothing. But in the unusual situation where this 120 volts shoots up above 150 volts, this varistor is going to clamp down on that voltage. Very often, it actually shorts itself out when this occurs. So if I was to have a short circuit right across my power line, this fuse will be forced to blow. So the varistor shorts itself out in the condition of a surge. Now, when can we have a power surge? Can anybody give me an example of when you might actually have a surge happen at your house? Jeremy? Okay, a power outage. So when the power goes out, and then when 10 minutes later or an hour later, Pico restores our power, sometimes you get that bright surge. Your lights go real bright. So that would clamp down on that. And depending on how high the surge is, it may even short itself out to protect everything after it in the power supply. Any other times we might have a surge, Andrew? A lightning strike. That would be a bad surge, right? You know, maybe lightning hits the power line out front and we get this big surge in our house, and hopefully it protects my very expensive computer or whatever my electronics is attached to. Now, you do realize when this MOV shorts out and blows the fuse, our device is still going to be dead, but only a couple of bucks worth of parts went bad instead of the very expensive parts, like, whatever this is powering, my 70-inch TV or my piece of industrial electronics or my super expensive gaming computer or whatever I have. So the fuse is an overcurrent device for protection, and the MOV would be an over voltage protection device. So our fuse protects from too much current, and our MOV protects for too much voltage. The next component that we have here, R1, is a 2.7 ohm resistor, and it might be a couple of watts. And when you look at this, you think, okay, so what in the world would a 2.7 ohm resistor do when I have 120 volts AC flowing through it? Well, that's not a lot of resistance, is it? It's not like we're going to get a lot of voltage drop across that. So what in the world could that do? Moses? Okay, so you're not wrong. If there's any excess current, you're thinking it's going to prevent that from happening. But isn't that what the fuse does? In case the fuse doesn't pop, is that what you're saying? Very good. This is a fusible resistor. It's in series with our fuse, and Moses called it exactly right. What if the fuse did not work? The main protection fuse, for some reason, does not work. So this acts like a backup for it. It's a fusible resistor in series with the main power fuse. Now, he said something that actually happens. Somebody put the wrong value fuse in. It's a 1 amp fuse, and they throw a 10 amp in there. Well, the engineers put a 1 amp fuse in there for a reason. And that reason is that this thing draws less than 1 amp normally, And if something goes wrong, it'll go over 1 amp. We're not going to re-engineer it and put the wrong fuse in. That creates liability for us as technicians. We have to always replace critical safety components with exactly what's supposed to be in there. But let's say somebody who does not know what they're doing says, oh, I know how to change a fuse. Let's pop a new one in there. And they put one that's too big. Well, guess what? It's not now meeting the normal safety requirements. So this acts like a backup for the fuse. It also does a second thing. It limits what we call in-rush current. Now, what is in-rush current? You've all observed it at your house. Large current devices, things like your air conditioner, central air, your microwave oven. You turn it on, and for a split second, you see your lights flicker or your lights just dim, just for a split second. That's because these devices sometimes require a bunch of current to get running. So you just see this little flicker. And what this resistor does is it kind of limits how much in-rush current there is. So not only is it acting as a backup for the fuse, it limits in-rush current when our device is first turned on. You know, when motors get running or capacitors charge up, where would we see this in the home? You know, appliances, higher powered electronic devices, like maybe you have 1,000-watt surround sound system and there's really big capacitors in the power supply. When you turn it on, you might want to limit this in-rush current. So this is a fusible resistor that is a backup for our main fuse, as well as limiting in-rush current. We have an inductor at the top and bottom of the AC power line. We also have a capacitor going to ground, a second capacitor going to ground, and a capacitor across the power line. So what are these guys for? Well, we've learned about alternating current. We've learned about reactants. So inductors, we know, exhibit inductive reactants, and capacitors exhibit capacitive reactants. So an inductor does what? An inductor passes what kind of frequencies and blocks what kind of frequencies? Inductors pass what and block what? Jeremy? Say that again. Okay, so an inductor will pass DC. And it also passes what frequencies at AC and blocks what frequencies at AC. Okay, so inductors tend to pass lows and block highs. Remember the formula for inductive reactance? X sub L equals, very good, 2 pi FL. So 2 pi, 6.28 times our frequency, 60 hertz. And then we have 100 millihenries. That's going to give me a pretty low reactance. As frequency increases, that reactance is going to rise. It's a multiplication problem. If I change any number in that 2 pi FL to a bigger number, my reactance is going to be higher. So higher frequencies get blocked. That inductor reacts to those higher frequencies, not letting them through. So these inductors act like low-pass filters. If any high frequency manages to squeak by these inductors, they're now going to get bypassed to ground or shunted to ground through these capacitors, because we know the capacitors do the exact opposite of inductors. So they pass highs and block lows. How do we know they do the opposite? Because the formula for capacitive reactance is 1 over 2 pi FC. So whenever we have a 1 over, we know that if we increase the numbers on the bottom, the answer is going to be smaller because we're dividing into 1. So 1 over 2 pi FC means as frequency increases, reactance decreases. So if a high frequency manages to push through some of these inductors, that remaining high frequency should be bypassed through ground to ground through these capacitors. Now this whole little series of parts, these capacitors and these inductors, have a name. Some engineers call it a line filter. Some engineers call it a line choke. Some engineers call it EMI or RFI suppression. But that's essentially what it does. It takes any interference on our power line that come from other devices. High frequency interference. Maybe your cell phone or your Wi-Fi is sneaking into this power supply. Well, we hope it blocks it out and filters that line. Motors from vacuum cleaners, appliances, power tools can generate noise on our power line. And this noise suppression or line choke device should help clean up our power line and hopefully have a nice 60 hertz clean AC waveform going to the rest of my power supply, because that's what we want. We don't want noise and interference on that. When I say noise, that's not an audible noise. That's usually, what we're saying is some sort of unwanted signal on our power line that should not be there. Usually it's electromagnetic interference. Here's our easiest component. Who could tell me what SW1 is for? It's a switch, and it does what? There we go. It completes the circuit and turns our device on, right? So right now we're all powered up to the switch. We're overcurrent protected, over voltage protected. We're cleaning up the power line. We have a clean 120 volts. We now flip the switch and send power to the primary of my AC power transformer, giving me 120 volts, 60 hertz, hopefully nice clean AC power. The LED and the dropping resistor are simply a power indicator. A little red light comes on, tells me I'm powered on. Here's a new one for you. I don't think you guys have seen this one before. TF2, 96 degrees Celsius. Well, that's kind of weird. But it's the schematic symbol for a fuse. So what does that tell me? What do you think that guy's all about? We've always talked about fuses, volts, and amps, right? But this is saying degrees. Sam? Very good. Sam called it a temperature fuse, and that's exactly what it is, Sam. We call it a thermal fuse. So essentially, it is placed on or in this particular power transformer. And if for some reason that power transformer runs too hot, it has a low temperature metal in it that at 96 degrees, it'll melt and interrupt power to the device. Now, where would you see this? Higher power devices. Think of a power amplifier. They usually have vents on the top and heat sinks, right? But what if somebody piled something on top of it? Would it have proper ventilation? No. Could it build up enough heat that something could happen? There's a situation the thermal fuse might blow. Anybody ever work on an old computer and when you open it up, it's full of dust? Well, there's a condition where, a fan is sucking in air to cool things, but now it's all clogged up with dust and dirt because it's many years old. Is it properly cooling? It's no longer properly cooling. The vents are blocked up with dust. So here's a situation where the overheat or thermal fuse might fail and protect us. Industrial equipment might have a thermal fuse in it. Now, I said might. Now, I want you to realize that everything that you see on the primary of this power supply might be there. Might be there. I can assure you every power supply has a fuse. It has to. UL, Underwriters Laboratories, those engineers that set standards that electronic equipment has to be built by, basically say we need fusible devices on AC powered equipment. So if something shorts out, it doesn't burn the home down. That's important. The manufacturer may elect or not elect to put an MOV in there. It depends on the cost of the product and how valuable it is and if we want to protect it. Line filtration. We don't need it. But if it's a piece of industrial equipment where it's important that it doesn't get interference, or a piece of medical equipment, biomed equipment might need line filtration to work well. But maybe your cheap computer monitor or cheap set of computer speakers, we don't care if that gets interference. It's not the end of the world. So the manufacturer may say, I'm keeping the cost down. I'm going to take that EMI suppression circuit out, that line choke. It'll still work. It just might get interference from other devices. And depending on how hot the device runs, it may or may not have that thermal fuse. So these parts are in here, to show the different things that we might do on the primary of our power supply to, protect it, to noise suppress it, thermal protect it. all these other these optional devices that the manufacturer determines, do we need to put them in there or not?